Hello, my name is Daniel Houston, and this is my Lab 5 magnetic braking with Faraday. In this lab, we will look at a magnet falling through a conductive tube of aluminum foil and model this interaction computationally. Here are a few formulas that we'll need to know throughout this lab. First, calculating the magnetic force, and then we have the derivative of flux due to time, and then we have the EMF equation, and then we have an equation for current, and then we have force on a loop. Now, for the setup of this experiment, we have the length of the tube to be 0.3 meters. We have the width of the foil to be 0.007 meters. The inner radius of the tube will be 0.02 meters. The outer radius will be 0.027 meters. The mass of the magnet will be 0.024 kilograms. And then the magnetic dipole moment of the magnet will be 3.206. And the average time it took the magnet to fall through the tube was 1.36 seconds. Now for the checkpoint questions, the first question is, why can't we use a Ferris tube, for example, a steel pipe? Well, the Ferris tube could become an induced magnet because it contains iron and would interfere with the experiment. And then what happens to the magnet? How does this compare to a magnet falling in free space without a tube? So through the tube, the magnet falls slowly, especially when compared to falling in free space. Now here's the first two parts of the code. The first part is a lot of the initial conditions that I said earlier, and then the second part is the magnetic field, and it's a function to create the magnetic field of the bar magnet. And here is steps 3 and 4 of the code, and step 3 looks at creating a function to calculate the magnetic flux, and it uses the function from d flux dt for each of the rings due to the falling magnet. And then step 4 looks at the calculation for the current in each of the rings. And this is steps 5 through 8. 5 and 6 looks at the force due to a loop due to the magnetic field. And then step 7 looks at the gravitational force of the magnet. And then steps 8 looks at the velocity update and the position update formulas due to Newton's second law. And this is the results of the computational model. And on the left, you can see the diagram of the model with the magnet falling through with the red and the blue color. And on the left, you can see the velocity versus time graph, and then the total time it takes for it to travel in the tube in seconds. And as you can see in the beginning, the magnet speeds up and then immediately slows down and then remains at a constant speed. And the magnet stays at a constant speed for about 1 second before exiting the tube. Interpreting the simulation. The intensity of the coloring of the tube indicates the magnitude of the current flowing through each ring. Red and blue indicate current flowing in opposite directions. Which color corresponds to the clockwise current and which counterclockwise? And how can you know? So you can tell that according to Lenz's law, that the red will be counterclockwise and then the blue will be clockwise, and this would be the forces to stop the magnet. And what happens to the dynamics of the system when you flip the magnet around? This would essentially do nothing, because the current would just flow in the opposite direction. And how does the total time in tube of the real-world system compare to that of the computational system? And how might this computational system be made more accurate? Well, the computational system was 1.432 seconds, and then the actual measured time was 1.36 seconds over 5 trials. So this is pretty close, and this is probably just due to air resistance, and the model on the computer could be more accurate with more rings. And how does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? And as you can tell from the diagram earlier, you could tell that in the first 0.2 of seconds, the forces were a little inconsistent, and then it remained constant for about 1 second, and then sped up after the second. And for the discussion questions, What if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? The gravitational would equal the braking force, thus resulting in the magnet not falling through the tube altogether. And what if holes or slots were cut into the tube? How would this affect the ring currents in your model? This would affect the flow of the current and cause an overall reduction of the braking force due to the reduction of this current. Thank you and have a good day.